So today I'm gonna talk about the bump tool and how you can use it in the JEDI system. So in the agenda, it was split into bump science and bump usage, but actually it will be more mixed, and it will be basically a big presentation of 1 hour split in two with a break in the middle for questions. Okay, this is the outline of my talk. I'm gonna talk about bump in general, and then speak more in details about the static B, then about the ensemble or hybrid B. I'm gonna talk about the Nika smoother, which is an important part of bump, and finally give you some tips to use bump for your applications. So let's get started with the bump overview. Um, just a quick reminder about what the B matrix is, especially in a variational framework where the background error covariance matrix B describes the uncertainty of the background XB. So here in the well-known cost function, it's just the B matrix is just the weight given to the first term, the JB term. And so if we look at this problem in another way, in the blue framework, B is actually the last operator applied to define the analysis increment. So for the second equation, XA, the analysis, is equal to XB plus B times something. So B basically defines the space of functions where the increment lies. So B is a complex and multivariate object containing complex 3D structures and potentially 40 if we look at 40 and var algorithms. Just a few basic facts about the B matrix. So it's a key aspect of variational DA systems, but in practice, we cannot have it fully estimated and stored, because if your state vector is maybe a billion elements, the B matrix would be a billion times a billion, so it's not possible to store such a big matrix. So we model it, and we just want to be able to apply it to an increment vector. B is a covariance matrix, so it must be symmetric and positive, or at least, yeah. And so we generally build its square root U. So B is equal to U transpose. And building U is a safe way to ensure that when we apply B, we actually apply a symmetric and positive or semi-definite operator. The usual covariance models are, so the static B, which is a sequence of parameterized operators, the ensemble-based B, which is a localized sample covariance matrix, or we can have hybrid modeling where we do linear combination of previous models. And all covariance models require a smoother to spread the information coming from the innovation. And so in most implementations, smoothers are grid specific, but for bump, we have the Nika smoother, which can work on any grid. So the hybrid background error covariance matrix, the simplest way to see it is just a linear combination between two terms. The first term is the ensemble term, and the second term is called the static term. So the first one, we have beta E squared, which is just a scalar weight. L is the localization matrix, which is applied with the Shor product. So the circle denotes here a Shor product. So it's an element by element product. And B tilde is a sampled covariance matrix sampled from an ensemble of forecasts. So this is our ensemble term, and the static term is just a weight, beta S squared, multiplying a static covariance matrix, BS, here in green. This covariance matrix itself is modeled as a sequence of operator. In general, it's done as it is shown here. So It's a symmetric sequence of operators where the outer operator is K, is a balance operator, so providing the multivariate aspects of the B matrix. Sigma here is the diagonal matrix of standard deviations, giving the weight to univariate. So it's a block diagonal matrix. It's a diagonal matrix, sorry. And finally, we have the C matrix in the center, which is just a correlation operator and which is a block diagonal. So BUMP stands for background error on an unstructured mesh package. And it's just one of the background error libraries we want to implement in Sabre, which is the system agnostic background error representation component of the JEDI project. BUMP works with any model grid and is able to take complex boundaries into account, as we will see. And this is an important feature for the ocean of our land models. It's written in modern Fortran, about 25,000 lines, and it can be called through Fortran or C++ interfaces. And the interfaces with BUMP are implemented for most JEDI models via the OOPS component. So in the functionalities of BUMP, you will be able to estimate and apply all the scalar and components we have seen before for the hybrid B. So we can estimate the horizontal and vertical localization length scale of L, the localization matrix, compute also the hybrid weights, beta E and beta S. We can compute vertical statistical regression for the balance operator K. And we can also estimate and filter objectively the standard deviation in the sigma diagonal matrix. Or each time between brackets, HDiag, VBOL, var, and so on are the names of the drivers that are doing these operations in BUMP. The horizontal and vertical correlation length scales of the correlation matrix can be also estimated either, as we will see in the HDiag driver just for the length scales, or we can also have anisotropic estimation using LCT, so local correlation tensors. Finally, we have a grid smoother, which is very important to apply either the localization or the correlation matrix in a variational framework. And here it's the NICAS smoother, and NICAS stands for normalized interpolated convolution from an adaptive subgrid. So we'll talk more about NICAS later in the presentation. So here is the BUMP credo, the BUMP main IDs. It's all about subgrids. So high resolution grids are great for model dynamics to get precise modeling of a small scale phenomenon, but it's very costly and not completely useful for background error covariance modeling, because in general, the size of the background error structures that we want to represent is significantly larger than the model grid cell size. So the leading IDs of BUMP are these three simple IDs. It's to use cleverly subgrids and to do all the costly operations on these subgrids and to interpolate the final results on the model grid. But the goal is to do all the important operation on the subgrid to keep the cost low. So now I'm going to talk about the static B, give you more details about how the static B is modeled in BUMP. So the static B is a robust and well-conditioned model of background error covariance, and it's based on a sequence of parameterized operators. These parameters can be defined using ensemble data over either a long period to give a climatological estimate. They can also be estimated over shorter sliding windows and be updated every cycle or every 10 cycle regularly anyway. the most common static B model, so as I said before, is this one with the balance operators, then inside the diagonal matrix for standard deviation, and at the center, the correlation operator, the univariate correlation operator. So bump can be used for all these operators. The balance operator can be quite complex and model dependent, depending on the model variables. But in bump, we have the vertical regressions, statistical regressions, that are that can be generically designed, so they can be used for any model, and they can be estimated locally and applied with bump. The static deviations that are in sigma can be also estimated locally and filtered to remove the sampling noise. And for the correlation length scales of the correlation operator, they are also estimated locally, and we'll see how. And then it's used to set up the Nika smoother, which is exactly normalized. It's important to have the diagonal at 1 so that we have a real correlation operator. So in the OOPS framework, all these static B components can come from either from bump or from your own model, or even from other components of the Sabre library. In the future, we hope to have more components in this library, and you can combine them as you wish. So here it is just a graphic to show you how we can do the static covariance training. So we start with an ensemble of forecasts, and we will first transform the variables to get the transform ensemble. So this transform can be, for instance, transforming the wind variables from U and V, the wind, to psi and chi, so the stream function and velocity potential, because it's easier to model the background error for these variables. So this is typically model specific. Then from this transform ensemble, we will compute the vertical regression using the VBAL driver, and this will produce the vertical balance data, so the K operator. We also use this transform ensemble and we apply the inverse vertical balance to it to get the unbalanced ensemble. That's the second step for VBAL. And then we will compute and potentially filter the variance fields of this unbalanced ensemble with the var driver. And this will provide the smooth variance field that is in the sigma operator. Then we use this unbalanced ensemble again to estimate and fit the correlation functions. So using either the HDiag operator that will provide just the length scale, so it will be isotropic, inhomogeneous but isotropic correlation functions, or we can use the local correlation tensors, the LCT, to get anisotropic correlation functions. And finally, we get these correlation length scales or local tensors and give them to the Nika's smoother. So you compute the smoother parameters, and so that we have a correlation smoother data that is required for the C operator, the C matrix. And so here we can see that the first task is model specific, but all the yellow box tasks here are generic tasks that can be done in BUM for any model. And and the gray box show the static covariance operators that are provided at the end of this training sequence. So here is an example of how to compute the vertical balance, so the vertical regressions. So here is for instance, the full model grid. It's the V3 cup grid at C180 resolution, and it's way too dense for what we need. So we will just choose a sample of points, and we will compute vertical covariances between cross covariances between variables for each of these subgrid points. And then here for the red point at the centers, which is an averaging center, a local averaging center, we will average the vertical covariances over a given radius. And here it's the dark blue points that will be averaged, and it will give the value for this center. And we will repeat this operation for many local averaging centers here, the red dots. And for each of these red dots, we have averaged vertical covariance, and we can compute the balance operator in a robust way. And then we interpolate the balance operator data on the model grid when we need it. So this was for the K operator, for the vertical balance. Now we can do the same, kind of the same for the estimation of the C operator, the correlation operator. So here it's the first set of origin points, but to compute the correlation functions, we will try to find some distant points, the green ones, and we will have increasing distances. And it's an isotropic sampling, so it's random angle. And for different increasing distance classes, we will compute the correlation, and we will do the same as before. We will average the correlation over a given radius for each local averaging center for each red dot. So here it what we get at 0 separation, and then we increase the separation, and we can average the correlations computed over these pairs of points. And so once we have the full correlation function for this red dot, for this local averaging center, we will, so this is the raw correlation function, we will try to fit it. So in BUMP, for now, we just have the Gasparian-Cohn 99 function, which is not the base choice here because it's a Gaussian-shaped function. And here, in this case, the correlation function was more peaked. So in the next few months, I want to implement other fitting functions that are more peaked to get better results. But so we get a fit with the Gasparian-Cohn function. And then from this Gasparian-Cohn, we have a support radius, which is the distance at which this function goes to 0, and it's a finite support radius. Once we have this correlation support radius, it's for a given local averaging center, but we can do the same for all the red dots we had before. So for each of these dots here, we have a given horizontal length scale. And finally, we can interpolate on the model grid and get a full field of correlation length scales or support radius here in this case. So this is how BUMP can use these subgrids to estimate correlation length scales fields. So I just showed how it works for the horizontal, but it's the same. Actually, it's a 3D estimation. It's also for the vertical. So just a summary of how to compute the correlation with the JEDI driver. So first, we define a homogeneous subgrid. It's the origin points. Then for each origin point, we find distant points for a series of distance classes. And for each local averaging center, we average the diagnostic values, so the correlation here, over a given radius. We compute the correlation. We fit this raw correlation function with a parameterized one. So here it's the Gasparian-Cohn, but it could be other functions to get the support radius. And finally, we can filter the correlation support radius on the subgrid because it's easier to filter spatially on the subgrid. And finally, we interpolate on the model grid to get a full field of correlation length scale. There is another way in BUM to compute the correlation functions, and it's using the LCT, the local correlation tensor. So if you want to have more details about the LCT, you can have a look at the Weaver, Anthony Weaver papers. It's mostly for the ocean. So here we have computed the correlation function on the model grid. So it's a very detailed one, and we can see that it's anisotropic. So this is estimated from the ensemble. And we will fit this local correlation function with a tensor. So it's just with a ellipsis, with a 2 axes and different length scales on the 2 axes, and also an off-diagonal component to give the tilt of the function. So this is at one location, but we will do the same at another location. Here it's the rho function, and here it's the LCT. So we can see that we can represent correctly the anisotropy. And we will do that for many points. It's always the same strategy in BUMP. We do that for a given sample of points, and then we interpolate the local correlation components on the model grid. So here it's what we get for the horizontal components. So interpolated over the model grid. The first one, A, it's in the zonal direction, B in the meridional direction, and C, it's the off-diagonal component. So this is interesting because for the ocean, for instance, it's important to have anisotropic correlation functions, for instance, at the equator or in places, other places, and for many variables. So here is just a summary of what we do with the LCT. We define a homogeneous subgrid. Then for each subgrid points, we compute the local correlation function on the model grid. And we fit this rho correlation function with a parameterized function that uses the correlation tensor, the local correlation tensor. And finally, we can also filter the LCT components to get smooth results on the subgrid, and we interpolate the LCT components over the model grid.